Okay, any answers? Okay, so according to your convention, see, this is an bubble, right? This is a not operation, right? If this is not there, for example, you have this, and you saw already, right? If that is not there, this D naught is equal to M naught only, right? Right. Here also you look at it. Okay, so you look at it. A is MSP. Here also A is MSP. That's very, very clear, right? It should be very much same. Okay, this is also MSP here, right? So D naught is M naught, but only thing is this complement is there. So I can write M0 complement. What is this? M1 complement. Okay, what is this? M2 just a minute, guys. Pigeons are. Okay, I'm sorry. Okay, can you guys hear me? Thank you, thank you. So this is M3 complement because just a not operation, right? So M4, M5, M6, M7. Okay. So you can have decoder in this way also, active low, active high, and all those stuff. Okay. Now what is coming to this? M1 complement, M2 complement, M4 complement, M7 complement, right? Now what is the output? Like for an AND gate, suppose if I have inputs like X and Y, you have X dot Y whole complement, correct? Similarly, you have 4. So M1 complement, M2 complement, M4 complement, M7 complement, whole complement. This is your F output, correct? Now we already know De Morgan's law. You have X dot Y whole complement is what? X complement plus Y complement. Now in the place of X, M1 complement is there. M1 complement whole complement plus M2 complement whole complement plus M4 complement whole complement plus M7 complement whole complement, right? So what is this? M1 plus M2 plus M4 plus M7. I can also write sigma M of 1, 2, 4, 7. So 1, 2, 4. Oh, option A and option D is same. Okay, no problem. This is a typo. Okay, so that's the answer, right? Sigma M 1, 2, 4, 7. Right? Okay, let me know through your chat box whether it is clear or not. Is this clear? Okay, thank you. Okay, try this next problem. It's a combination of decoder and mux. So this is a 2 by 4 decoder. This A is MSP, B is LSP, and this is a NAND gate. This is a AND gate. This is 2 by 1 mux. What is the Y? Numerical answer type. Okay, any answers? So very simple. Uh, you need to observe this very clearly, right? So A is MSB, B is LSB, right? So this is the combination. Okay, A is MSB, B is LSB, right? So A is 1, B is 0. Okay, if you convert it to decimal, base 10 means this output, wherever 2 is there, this output is 1, remaining will be zeros. That's all, right? This is what we saw in the previous class, right? Now we know NAND gate. What is NAND gate? 0 and 1 complement. 0 and 1 is 0. 0 complement, that is 1. AND gate 0 and 0, that is 0, right? Now this is one in to this input. This is the 1 is coming here. 0 is here, and 1 is applied as a select line. 1 is applied as a select line. When 1 is applied, this will be chosen. This select line will be chosen. I mean, this input line will be chosen, pass it to output. That's how mux work, right? We have seen extensively in the last week how the mux works and all. So, what is the y value? Y is 1. Oh, hey guys, you guys need to be on time, right? So, this is about 2 by 4 decoder. What is next is an encoder, okay? So, this is just quite opposite to this, right? Now, what is decoder does? Binary to discrete. What encoder should do? Opposite. Discrete to binary. So, how it will happen? So, you have a decoder here. If at all I have to configure it, I should write it as 2 by 4, 3 by 8. Means that many combinations are possible. Like that, if I have n inputs, I have 2 power n combinations that are possible at the output side. Similarly, for an encoder, it is opposite, 2 power n by 1. It has to do exactly opposite of the decoder. Right? Let's say I'll take 4 by 2. No select line, right? So 0, 1, 2, 3. So here it should be very much careful. Which is MSB, which is out MSB, right? Let's say MSB. This is LSB. Let's say Y1, Y0. Correct? Here I0, I1, I2, I3. Correct? So let's see how this works. Right? I'll draw the truth table. Also, we have seen the difference between truth table and characteristic table, right? Okay, these are outputs. These are inputs. I0, I1, I2, I3. If I0 is 1, okay, remaining all are zeros. Okay. Now, what is this 0? That will be decoded here. 0, 0. Similar, same thing. Then 0, 1, 0, 1 will be encoded. 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, 1, 1. That's all. See why I wrote this? Because these are the only thing possible, right? You see this here for the decoder. 0, 0, this is possible. 0, 1, this is possible. 1, 0, this is 1. Okay, same thing I'm doing it here also. Correct? So next question is, if at all I want to write the Boolean expressions for y1 and y0. Okay, in terms of I0, I1, I2, I3. What is y1? Y1 is, I can simply write it as I2 plus I3. You see this here, whenever I2 is 1 or I3 is 1, y1 is going to be 1. And what about y0? Y0 is 1 when I1 is 1 or I3 is 1. Okay, so I can write I1 plus I3. One can use K-maps also for that, and then use don't care conditions for the combination that doesn't exist here, and then one can solve it. Okay, simply I can write like that. Okay, so if I realize y1 is I2, this is OR gate, right? This is y1. Y0 needs one more OR gate. Y0 is one more OR gate. I1. Okay, so this is how you can realize. It's simple. If you have two OR gates, just two input OR gates, I can realize 4 by 2 encoder. It's not a rocket science, right? Simple. So here the only condition is, this is the condition. If I see, if one of the input is 1, remaining all should be zeros. Okay. Only one input, only one of I0, I1, I2, I3 needs to be 1, remaining all to be zeros. Are getting it? Now, suppose by mistake, let's say for example, I do some kind of iteration like this. Okay, just a minute. You can have priority, you have encoders in your systems, in your laptops and all, where you have a keyboard. When you press something, something will be decoded and inside something happens. Or otherwise also, no problem. Let's see, for example, if I take 0, 0, 1, 0 as an input, okay, I0, I1, I2, I3. What is output? Y1, Y0 is like 1, 0, right? Now, this is what I expect. Now, for example, for some reason, this I3 got corrupted. Okay. So, if I write 0, 0, 1, 1, what is my output? Y1 and Y0 is, because if I3 got corrupted, these gates doesn't know. So this doesn't know. These gates, they perform their job, but I3 got corrupted in the process. Because of that, result got corrupted. Are you getting it? Right? So using a normal encoder like this is very, very tedious job. That's why we use something called as priority encoder. Now name suggests the same thing, right? You give a priority to some inputs, right? Suppose if one of the input is 1, irrespective of other inputs, okay, doesn't matter what happens to other inputs, your y0 and y1 will show something corresponding to I3, right? So that we will see in the, I think we have a priority encoder problem. There we will discuss in detail about priority encoder. Now you understood this problem, right? So this is the biggest disadvantage, okay? This is the biggest disadvantage with the encoder, right? We will try to sort out that one in the next problem. Hmm? Okay, meanwhile, you can solve this problem now that you know what is a 8 by 3 encoder. Most of you might have already studied. So just I want to give a recap so that you guys are all on my page before we go for the priority encoder. Any answers? Okay, Shashikant is asking, is there any schedule which we are following here for sessions, like which topic first and so on? This is my first and I want to prepare for all future sessions, so please tell me. Uh, okay, Shashikant, actually there is a schedule that you can see. I think right now you can see my screen, right? Here you can see the kind of topics that we will be discussing. Okay, so today is going to be digital circuits, combinational circuits part 2. They didn't update it here. Then next session onwards, we will start with uh, you know uh, sequential circuits like resistors, flip-flops, all those things. Okay, latches, flip-flops. Then we'll move on to counters. Then we'll move on to shift registers. Then static timing analysis, and so on so forth. You can watch the recorded sessions. These all are recorded on my YouTube channel. Okay, and that link is also they have given already, right? Here you can click on this link, right? And then you can watch the previous videos, what happened, and all those things. Then you can be on the same page with all of us, right? Now, see, somebody said some answer, right? I forgot. I didn't get that. B. Okay, B for Bombay. Okay, fine. Now this is 8 by 3 encoder. We all know that this is only this input line is 1. What is this number? 5, right? This 5 has to be encoded, right? How is it? This is y2, y1, y0. Sir, why did you take this as MSB? Because of this. Higher number will be like MSB, right? This should be considered as MSB. This should be considered as LSB. So what is 5 as decoded as 101 in the binary, okay? 1, y1 is 0, y0 is 0, y0 is 1, sorry. Now, this is a 3 input XOR gate, right? 0, 1, A, and this is output here. Like, and again you can say y2 is 1, y1 is 0, y0 is 1. Okay, so which line it will choose? 1, 0, 1 means this one. What is this connect? Where is this connected to? Connected to the output of this gate. Okay, so you have 0 XOR of 1 XOR of A. Okay, so I can say 0 XOR of 1 is 1, correct? 1 XOR of A is A complement, right? You can write the simple equation, right? X XOR of Y is what? X Y complement plus X complement Y. So 1 A complement plus 1 complement A. So this is 0. This is going to be A complement, right? That's what is, right? That's the option B. Right? This is XOR operation. Now, here the concept of priority encoder comes. Okay. So, I just want to summarize once again, like 1, 2, 3, 4 lines. Output is 2 lines. I0, I1, I2, I3. So, if I write I0, I1, I2, I3, Y1, Y0, we already know these are the combinations that are possible. I mean, we are only allowing these combinations for it to work as a proper, encoder. Now, how does priority encoder works? I just want to tweak it a bit. Same inputs, I0, I1, I2, I3, and we have also seen the issue, right? When one of them gets corrupted, then everything will be corrupted to the output side. So what we do is we give priority. We say I3 is more prior, I2, then I1, then I0. What does it mean? More priority, correct? More priority. What does it mean? Now let's look at the truth table. Suppose if I3 is 1, doesn't matter I2 is 0 or 1. Doesn't matter I1 is 0 or 1. Doesn't matter I0 is 0 or 1. Output will be showing corresponding to 3 only, like 1, 1. So what is this called as? Doesn't matter means what? don't care, don't care, don't care. Yes or no? Very simple topic, such a simple topic, right? Output does not depend on I2, I3, I2, I1, I0. Okay, output will just corresponding to I3. Now, let's say I3 is 0, then if I2 is 1, doesn't matter what is I1 and I0, output will be corresponding to 2. Now, I3 is 0, I2 is 0, then I1 is 1, then I0 is don't care, it doesn't matter, then output will be corresponding to I1. Now, I3 0, I2 0, I1 0, then if I0 is 1, then only output will show 0 0. This is how a priority encoder works. Now, accordingly, you can find out what is y1 in terms of Boolean equations. I2, I0, I1, I2, I3. Y1, Y0 also in terms of. But this is the basic difference between a encoder and a priority encoder. The moment you see this priority, first you have to check whether I3 is 1, then move to I2, then move to I1, then move to I0. Accordingly, output, already outputs are like 0 means if, already if I0 is 1 means 0 0, right? Now its priority is more, I3 is having highest priority, so first you will check I3. Because I3 is 1, so you will decode this 3 as 1 1 1, right? Output. That's how simple it is, right? So in this case doesn't matter. In this encoder case, it really doesn't matter. Okay, it works on the principle of this. Okay, this principle, right? So here we put a condition that okay, only one of the input is 1, others are zeros. Okay, that's a basic condition for the inputs, right? Okay, this is the basics of priority encoder. Now you see this problem. And these days, a lot of problems on priority encoders are coming up. So let's see. So according to the problem, the priority is given as C is highest priority, then D, then B, then A. If K is 0, M is 1. Okay, if K is 0, M is 1. What are the values of X and Y? And they clearly said it is a priority encoder. C is connected to line 2. This is line 3. B is line 1, line 0. Any answers? Okay, Madhurity, you asked, what if all the inputs of encoder are 0? See, when this is not a functionality of an encoder, right? So for example, we can say, uh, okay, let's go here. Where is the encoder? Right here. So let's say you are saying, what if all are zero, right? Now it's up to you what you want to pull these pins to, whether you want to drive them to high impedance state, right? Because that is only possible because 0, 0, 0, 1, 1, 0, 1, 1 is not existing, right? You can say one y1 is 1, another one is high impedance. One is high impedance, another one is 1, right? So these three combinations you can choose. Okay. Am I clear? So guys, if you have any questions, you can just unmute yourself and then ask so that I might sometimes may not see the comments. Okay, let's look at this problem now. K is 0, M is 1. Okay, K is MSP, this is LSP. Okay, thank you. Option D, somebody is saying option D, somebody said option C. Let's see. LSP, this is 0, 1. This is, if you convert it into decimal, this is 1. Correct. Means this particular line will be 1. Remaining all will be 0. This is a basic decoder, right? Now here what happened? 0, but the input what you are getting is 1, right? Because this is 0 complement. Here 1. Sorry, 0. Right? Because this line is already 1. Here it is 1. Here it is 1. Right. Now you can see what is the first priority C. That line has become 1. Yes, you already received 1. Because you received 1, output will be decoded as this one, right? 2. 2 will be decoded at the output side. I mean encoded at the output side. I'm sorry. So what is MSB? MSB is Y, correct? Y is MSB. X is LSB, right? So 2, how to write it as in the of binary? 1, 0, correct? So X is 0, Y is 1, right? Okay, are we clear so far, guys? Say yes or no in your chat box. Okay, Bunty, what's your question, Bunty? Okay, so simple, right? You have a decoder, right? 2 by 4 decoder. Now the inputs are given MSB, LSB. K is MSB, M is LSB, right? Now 0, 1 will give these as outputs 0, 1, 0, right? Now this is not directly given to the priority encoder, right? There is a NOT gate here, you see, there is a NOT operation that is happening. So the output of the NOT gate will go to the lines 0, 1, 2, 3, where the lines are 2 is nothing but C, then D, then B, then E. That's how it is, right? So now for the priority encoder, how the priority encoder works on the priority of C, D, B, A. First it will check for C, whether it is 1 or not. Yes, it is 1. So the output will be shown in accordance with the line 2, right? So 2 is there, right? How the 2 will be encoded as 1 and 0. This is where MSB is 1, LSB is X. I mean MSB is Y, LSB is X. Right here, if you see, MSB is connected to Y, X is connected to the LSB. Are you getting it? So 2 can be encoded like this, 1, 0. So according to this, x is 0, y is 1. Little bit of tricky problem actually. We will check for active low or active high for priority. Doesn't matter because they mention, uh, until otherwise they mention, it is going to be active high. Here it's a basic decoder, right? Otherwise, they will clearly specifically mention in the problem it is active low or active high. But you need to unmute and then ask, okay? I'm not able to understand exactly what you're trying to ask. Suppose if your question is in the structure, see, I can also write the structure like this, right? You have a decoder. Same thing, no? You can treat this as there is a some NOT gate between decoder and the encoder. Okay. Still the functionality of the encoder will be same, right? Are you clear, Bunty? Okay, all right. So if they want to mention, they'll clearly mention in the problem whether it is active low or active high. Okay. Okay. This is one of my favorite problem because it comes with some finite real-time resemblance. So what is it is there are three NOT gates and then there is an AND gate. Okay. And the signal test. This is the signal test. This is the signal test, which was at low. Okay. Initially, okay, test was at low. You switch to high and maintained high. Okay, like this. What will happen to the output? Whether output will stay at 0 or stay at 1 or pulses from 0 to 1 and 1 to 0 and pulses from 1 to 0 and 0 to 1. And assume that all the gates have identical non-zero delay. Here that is a problem. So the gates will come with a delay. B for Bombay or D for Delhi? Okay. Very nice, man. Thank you so much for unmuting yourself and then answering it. Okay. So that I don't need to go back to the chat. Great. See, if you look at this no, if let's say for example, zero delay if you consider, that means if there is a change in the test, that will reflect everywhere instantaneously, right? So actually, if you look at this NAND gate with a zero delay, let's say this is not right. This is test. So one input is test, then this is test complement, this is test double complement, test triple complement. Okay. So test triple complement is test complement, right? So the output is what? NAND gate, no? One input is test, another input is test complement, whole complement. Test in test complement is 0, so 0 complement is equal to 1. So the answer is 1. If it is 0 delay, because it reflects everywhere. But question is not that. Question is, it has a non-zero delay. So what is non-zero delay? Let's assume something. These are not very difficult problems, okay? But only thing is they look like that. This is test. Okay. So initially, okay, was at low, correct? It was 0. That means that this would have been 1, correct? That means that 0.1 whole complement is 1, right? Initially it was 1 when test was at low. Now what they did, okay, this is a stable state, right? This is a stable state. Suddenly they made it to 1. Okay. Now will all the outputs change instantaneously? No. Right? We know the first stable state. Then what happens? Now it has become, test becomes 1, right? Means that is reflected here. Let's say everything has 10 nanoseconds delay. 10 nanoseconds. 10 nanoseconds, right? Now let me draw the time graph. This is versus time. This is output. Now this is 0, right? 10 nanoseconds, 20 nanoseconds, 13. Oh, sorry, I am congesting the slide. Guys, give me a time. Okay, just a minute. Simple concept. You don't need to worry much about it. Okay, you will understand this. I just want to draw it so that any problem comes something like this, you can draw this timing diagram and then try to get that. Okay, this is output versus T, right? So initially, what is our output? 1. Now let's say at T equal to 0, right? Test has been changed from, which was at low, he switched to high, right? This was at low, switched to high and maintained at high. Now this is 1, right? Let's say this input is X, this input is Y. Now X will become 1 instantaneously when test equal to 1, but Y, right, is still at 0, correct? What is your output here? Output is X dot Y whole complement, right? So what is my idea is, Y is a triple complement of test, right? When you made suddenly test from 0 to 1, ideally Y will take what? Y is equal to test complement after 30 nanoseconds. X equal to test immediately. Correct? Output is equal to what? X and Y whole complement after 10 nanoseconds. Yes or no? Right? So the output will take 10 nanoseconds once it knows the inputs X and Y. Right? So since X has become 1, correct, instantaneously. So how much time does the Y will take? 30 nanoseconds time, right? So what is output after 10 nanoseconds? Value of X is 1, value of Y is still like previously how much was the value of 0? I mean value of Y? Correct. So See, very simple. What I'm saying is when test was 0, I'm just calculating the initial state. Okay, just give me a second. Okay. Now we have set up the equation, right? So y is this much after 30 nanoseconds, y x equal test immediately, output is this much, right? So let's study. When test was 0, x is 0, y is 1, correct? Now you computed 0.1 whole complement, that is equal to 1. So we have plotted output y equal to 1. Now let me compute. Test has become 1. X will become 1 instantaneously, right? Now, will the y become 1 instantaneously? No. Y will take 30 nanoseconds to become 0. Even though y equal to test complement, correct? Right? Even though y equal test complement, it will take 30 nanoseconds to become 0. It will not become instantaneously. So, in the process, what will happen? Your x has already become 1, y is already 1, correct? So, the output will be what? 1.1 whole complement equal to 0. This is after 10 nanoseconds, right? So, after 10 nanoseconds from 0, right, output will become 0, correct? Now, after 30 nanoseconds, y will become 0, correct? Once y becomes 0, again output will be recomputed, correct? Because the value of y is changed, correct? So, 1, because now the value of x is 1, then 0 whole complement. So, the output is 1. How much time? After 30 nanoseconds, right? After, okay, this is 30 plus this is 10, 40 nanoseconds, right? From this 30 nanoseconds extra again to become 1. Okay. So it was 1, then because of non-zero delay, it has become 0, then again it has become, come back to the 1, right? So 1, 0, 1. See, what we did is we computed when test equal to 0, what are the values of x and y. Now, when the test changes to 0 to 1, y doesn't change instantaneously. It will take 30 nanoseconds to change. But x has changed already because it's immediately connected to test. So the output will be changed to momentarily 1.1 whole complement, that is equal to 0. Now, after 30 nanoseconds, y changes. Because again y changed, output will be recomputed. Okay, how much time it will take? 40 nanoseconds, right? Overall, right? If you look at it. So, if you look at the overall time, see, this is 0, this is 10, this is 30. So, output will take 40 nanoseconds time, okay, to change to 1 again. So, this is a momentarily 0 here, and again get back to 1. Right? So, what is the answer? Option D, pulses from 1 to 0 to 1. Okay, guys, are you guys clear? Simple, no? Right? So, next. Now, since we have decoder, mux, encoder, all those things, we have a combination of decoder and mux. Solve this problem. The previous problem, which I was talking about, this problem was typically little bit of complicated, little complicated. Okay. Otherwise, it's everything is simple, right? Come back to this problem. What is y? You have a decoder and you have a 4x1 mux. Okay, option D. So what is this D naught? See here, this is MSB, right? This is LSB. Yeah. So this is P bar A bar. What is this? P bar A. P A bar. P A. And we know output equation of a mux, right? S1 complement, S0 complement, I0. S1 complement, S0, I1. S1, S0 complement, I2. S1, S0, I3. Right. So we know already S1 is P, S0 is A. So I'll take this B complement A. Then what is I0? B complement A complement plus B complement. S0 is A. I1 is B complement A plus S1 is what? B A complement. What is I2? B A complement plus S1 is B, S0 is A. What is I3? B A. Correct? So this is B complement A complement. B complement A, B A complement plus B A. Right? From these two B complement, this is B. B complement plus B is 1. Option D is the right answer. Hmm? Yeah. Output wave. Okay, this is the output. Okay, has a frequency of 10 megahertz. Output frequency is 10 megahertz. Propagation delay of each inverter is dash. See, this is back-to-back connection of an inverter, right? So this output will be either 1 or 0. But what they are saying is output wave has a frequency of 10 megahertz. So what could be the propagation delay of each inverter? Something similar to what we have seen in the just before, one slide before, right? This problem. See, for example, you can assume anything. Output can be either 0 or 1. That's all right for a digital circuit. Now, let's say, for example, this is TP, right? All have a equal propagation delay of TP. Let's say this is TP, right? Now, this 0 will become 1. Then this will become 0 because not operation. This again will become 1. Then this one will be here. This one will become 0. Then again 0 will become 1. Correct? So you have 0, you got 1, right? How much time the 0 will be there? Like that? TP, 2 TP, 3 TP, 4 TP, 5 TP, right? Then again 1 will be there for 5 more TP. Then it will become 0. Then again it will become 1 and so on, right? Now, is it not the frequency? This is time period, right? Time period is 10 times TP. What is frequency? We know 1 by T, right? So 1 by 10 times TP is what is given as 10 megahertz, right? 10 into 10 power 6 hertz. That is 1 over 10 TP. What is TP? 1 by 10 into 10 power 7. This is nothing but 10 power minus 8 seconds. Okay, right? I can write 10 into 10 power minus 9 seconds, 10 nanoseconds, right? Option D is option B. Sorry, B for Bombay. The right answer. Is this clear, guys? Okay. So these are the typical problems that I found in you know previous gate questions and all, which I thought that maybe you need to refresh on this so that it will be proper. Right. Do this one. Minimum number of two input. I mean minimum number of 2 by 1 muxes are required to implement 2 input OR gate and 2 input XOR gate. You need to use only muxes. Minimum number of 2:1 muxes required to implement a 2 input OR gate and 2 input XOR gate. Shall I continue 5 more minutes? Maybe one more problem is there. Oh, 2 more are there. Can I take 10 more minutes or how is it? You have any other class or something? So that we will wind up all the combinational this week itself. Say yes or no in your chat box. 6 o'clock? Okay, no problem. Then you try this. These three I just give you as a homework. Okay. So I will display this in the recorded video for 1 minute, 2 minutes so that you can just go through these problems. And then if you have any questions, you can ask me. I'm not going to discuss this in the next week. Okay. But you can see them in the recorded session. Just pause that video and then you can just see these problems. Or you can ask me over mail so that I can reply. Okay, my mail is this. Right. So anyways, it's recorded. If somebody want to solve it and if you don't have any class, then we can continue. Right. Anyways, we'll complete that. And the other people who have a class, they can see the recorded video. So 2 by 1 muxes, right? That's what they're asking. 2 input OR gate, 2 input XOR gate. So this is a simple technique that you can use for OR gate, right? I mean, for realizing any function using mux, right? Let's say this is y. You know OR gate, right? 0, 0, 0, 1, 1, 0, 1, 1. OR operation 1, 1, 1, right? Now we have already seen this extensively in the last class, how to find the inputs, right? You can choose select line, right? Let's say I'm choosing select line as B. You can choose select line as A and then still solve the problem, right? Or I can choose select line as A. Anything is fine. If A is 0, what happens? You see, Y is not constant, but it is changing 0 and 1. Means it is just reflecting a B, right? If A is 0, Y is going to be B. You observe A equal to 1, Y is always 1. Irrespective of B, Y is 1. Right? So, this is nothing but a OR gate. Similarly, one can try with the B also as a select line. Okay. So, how many muxes are required? Only one mux, right? One mux is sufficient. Now, let's go for XOR operation. Zero 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 1 1 0 1 1 0 1 1 0. Same concept, nothing changing, right? If A is 0, what happens? If A is 0, correct, Y is going to be B. If A is 1, you see, if A is 1, Y is 1 0, it is not same, but it is complement of B. If B is 0, Y is 1, if B is 1, Y is 0. So it's a complement of B. Now here is a mistake people does. They think only one mux is required. No, rot. You know what is this B complement? Right. So you just have available, what are available inputs? Available inputs are A and B. B complement is a not available input. So you have to generate B complement. For generating B complement, you need one more mux. Correct? How to generate? Not gate using mux. Same procedure. What is not operation? B complement, right? If B is 0, then this is 1, this is 1, this is 0. So if I take 2 by 1 mux, okay, only one input, so no problem, only one input on select line, right? If B is 0, output should be 1, correct? If B is 0, output should be 1, right? So you select 1. You give input as 1 here. Obviously, the other one is 0. So now you are ready with the B complement, right? This is B, this is 0, 1, this is 1, 0. If B becomes 0, 1 will be passed. If B equal to 1, 0 will be passed to the output, okay? So how many muxes are required? 2 multiplexes are required for XOR. OR gate 1, XOR gate 2, okay? Option A is the right answer. Okay, then this is how you need to do next problem. Here a combination of NOR gate, NOT gate, muxes, everything is there, and the delays are also given. This is more practical problem than a gate question. It's a more practical thing, and it's also a gate question. What you need to find is the longest possible time delay between inputs and outputs. They mentioned PQRST. PQRST are inputs, Y is the output. Delay of NOR gate is given 2 nanoseconds. Delay of NOR gate mux is 1.5 nanoseconds. This is 1.5 nanoseconds. Then NOT gate is 1 nanoseconds. Okay. So what could be the longest possible time delay between inputs and output is dash nanoseconds. Six nanoseconds. Okay, let's say, see your Y is decided by T, right? Okay, if T is 0, for example, what will happen? What is the delay between inputs and outputs? Let's see. Then we can calculate T equal to 1, what will happen? If T equal to 0, this is 0, this is 1. Of course, there is 1 nanoseconds delay. Let's see whether it will come into the picture or not. Right? If t equal to 0, right? T equal to 0, uh, this Q and R, right? T equal to 0, this branch. I mean, you need to calculate the value at this point. Then this is 1, means you need to calculate the value at this point. All right? So to calculate value at this point, I need to depend on this. To calculate the value at this point, I need to depend on 0, correct? Right? To calculate at this point, I need to depend on this gate, right? So how much time? NAR gate is how much? 2 nanoseconds. Then to propagate this output from here to here, how much time? It will take 1.5 nanoseconds. So overall, till this point, you took 3.5 nanoseconds, correct? Then after that, this will take how much time? This will not take any much time, right? This is 3.5 nanoseconds because the output, this is the output node, na? This is how the output is traveling, right? Correct. So this NAR gate may not come into picture. So this multiplexer has again 1.5 nanoseconds along with the 3.5. So your Y will be 3.5 nanoseconds plus 1.5 nanoseconds. Okay, it's a 5 nanoseconds. Now, sir, what happened to this one? See, when you apply t equal to 0, by the time these inputs reaches this point, this is 3.5 nanoseconds. This t would have already become 1, right? It's a parallel processing, na? Correct. If you apply all the inputs P, Q, R, S, T at the same time, by the time this Q, R reaches this point, it is already 3.5 nanoseconds. Correct? Yeah. I think one more problem is there. We will just see if there are anybody who, and then it's a recorded video. You can, it is available. Actually. It will take 5 minutes extra. Okay. Yeah. So by the time this QR output reaches this point, 3.5 nanoseconds, it's already become 1. So you don't need to count this 1 nanosecond. Okay, it's a parallel processing thing happening, right? So if I choose t equal to 0, I need to wait for 5 nanoseconds for the output. Suppose if I choose t equal to 1, that means what? Right, now I'll change the color. First, I need to identify the path, which path the output will, I mean, inputs will travel. T equal to 1 means this path. This is 0. Okay, this is 0 means this node I need to know, right? So if I choose this, this output, this will go like this. Okay, along the green. So along this path, right? NOT gate has 1 nanosecond. Then this MUX has 1.5 nanosecond. Plus again this NOR gate has 2 nanosecond, right? Because along this path, this NOT gate is there. I mean this NOR gate is there. Then again MUX 1.5 nanosecond. Okay, this is the delay that you expect. Okay, what is this? 3 plus 2 plus 1, 6 nanoseconds. Okay, this is the longest part, 6. Apart from that, nothing else is there, right? Okay, this is the last problem of the day. So in the figure, what is the question is, in the figure LED, this is LED, emits light when S1 and S2 are closed. You need to find out when the LED is going to emit the light. Emit light when S1 and S2 are open. Emit light when S1 is closed and S2 is on a different combination. Only one of them is closed or it doesn't emit at all. So for this, what you need to find, what you need to see is, for this LED to glow, okay, this should be in forward bias. For that, The other side, see, one end is 5 already, right? This side should be 0. If there is 0, then obviously the LED will be forward bias. Now to make it 0, what should happen? That we need to check. Okay. Now if you look at this NAND gate, right? This is NAND gate. One strange thing with the NAND gate is, if at all you want the NAND gate output to be 0, right? Both the inputs, X and Y, both should be 1. Okay, this is X, this is Y. Both should be 1. Correct? And let's see whether it is possible or not. Then only it will emit, right? Then only it will emit. LED will emit. So X, this is AND is connected to S1 and S3 to S2. XR is connected to S2 and the other input. What is this input? This is connected to 5. Means this logic is 1. Right? To make Y equal to 1, that means, right, this S2 should be 0. Correct? This needs to be 0 such that Y will become 1. If this is 0, you see this is connected to AND operation. This is 0, the output is going to be 0. Correct? To make Y equal to 1, okay, S2 equal to 0. If S2 equal to 0, that will make sure that X equal to 0. Right? This is only possible. Right? To make Y equal to 1, S2 has to be 1. S2 has to be, sorry, if to make Y equal to 1, S2 has to be 0. If S2 is 0, the output of this AND gate is going to be 0. Right? Is it possible? X equal to 1, Y equal to 1, not possible. That means what? LED never emit light. That's it. Correct? So option D, right, doesn't emit light irrespective of the switch positions. If you make S2 equal to 1, then obviously Y equal to 0. No need to think about that also. Correct? It's always there. So LED never emit light. Okay, that's all guys from my side. Now we will conclude the session. Thank you. If you have any questions, you can ask me.